All right, today we're going to talk about the invisible science that keeps our entire world from, well, falling apart. It's officially called structural analysis, but I think a better name for it is simply the science of not breaking.
I mean, have you ever really thought about it? You stand at the bottom of a skyscraper, or you're driving over a massive bridge, or maybe you're just sitting in an airplane, and you just have to wonder, how does all of this not break? How are we so sure that these enormous, complex structures are actually going to hold up? Well, that's the big question we're diving into.
You see, everything we build is in this constant invisible battle. It's fighting against enemies you can't even see. There's the sheer weight it has to support. Engineers call that load. Then you've got these internal forces trying to pull it apart from the inside, which is known as stress. And on top of all that, there's the constant shaking and rattling from things like wind or traffic, which we call vibration.
So here's how we're going to break it all down. First, we'll look at those invisible forces. Then, we'll get into how we actually decode them. After that, we'll check out the amazing digital tools engineers use, see some incredible real-world examples in action, and finally, wrap up with why this stuff matters so much.
Okay, first up, the invisible forces. It makes sense, right? If you want to build something that doesn't break, you have to start by understanding exactly what's trying to break it in the first place.
So how do you even begin to fight these forces you can't see? How can you possibly predict what they're going to do before it's too late? Well, the answer is all about decoding the strain. It's this incredible science of turning those invisible forces into very real, life-saving predictions.
And that science has a name: structural analysis. The textbook definition is that it's the discipline of determining the effects of loads on physical structures and their components. Pretty straightforward.
But let's just cut right through the jargon. At its core, structural analysis is all about one mind-blowing thing. It's the science of predicting the exact breaking point of something before you even build it.
So how do modern engineers pull this off? How do they predict the future? Well, they use a kind of digital crystal ball. It's a revolutionary technique called finite element analysis, or as everyone calls it, FEA.
The whole idea behind FEA is just brilliant. You break it 1,000 times on a computer so you can be sure it never ever breaks in the real world. So what the software does is it takes this super detailed 3D model and slices it up into thousands or even millions of tiny little pieces called a mesh. And by analyzing the forces on every single one of those tiny pieces, it can predict with incredible accuracy how the whole thing is going to behave under just about any stress you can imagine.
It really just comes down to this four-step process. First, you get that detailed digital model. Second, you apply all kinds of virtual forces, simulating everything from the weight of a bridge full of trucks to the vibrations of a rocket launch. Third, the computer does all the heavy lifting, calculating exactly where the biggest stress points are, the weak spots. And finally, and this is the magic part, engineers use that information to optimize the design, adding a little strength here, maybe taking away some unneeded weight there to make it perfect.
Okay, the theory is cool, but let's see where the rubber meets the road. Welcome to Analysis in Action. You're about to see how this science is the secret ingredient behind almost everything we use every single day.
Let's start big. I mean, really big. Floating wind turbines. These things are some of the largest moving structures humanity has ever built. And we put them out in the middle of the ocean, one of the most chaotic places on Earth. Failure is just not an option.
So to make sure these giants can survive for decades out there, engineers use FEA to analyze, well, everything. They test tons of different structural shapes to see what works best. They study how the whole thing sways and bends in the wind. And they simulate a whole lifetime of abuse from the environment. We're talking monster waves, hurricane-force winds, you name it, to make absolutely sure it's safe.
Now let's go from something absolutely massive to something critically small. Think about it. We trust elevators with our lives. And that trust is built on the careful structural analysis of tiny but vital parts, like the gears inside the motor.
And here, the analysis gets super specific. They look at things like von Mises stress, which is just a fancy way of predicting the exact point where a piece of metal will bend and not spring back. Like when you bend a paper clip just a little too far. They calculate every single twisting and bending force to make sure these small parts can handle massive loads, meeting safety standards that go way beyond anything they'll ever face in real life.
And this science isn't just for big chunks of metal. It's what allows us to push the boundaries with really advanced materials, like, say, a high-speed rotor made out of carbon fiber.
You see, the tricky thing with carbon fiber is that it's not one solid piece. It's made of many thin sheets, all layered and bonded together. So stress flows through it in really complex ways. Using FEA, Engineers can literally map how forces move through each and every one of those layers. This lets them create parts that are both unbelievably strong and incredibly lightweight.
So we've covered the what and the how, but let's bring it all home and talk about the biggest question of all. Why does any of this really matter?
Well, it comes down to solving this fundamental puzzle that every engineer faces, this constant tug-of-war between strength and weight. On one hand, you need your structure to be strong enough to handle anything you can throw at it, but on the other hand, you want it to be as light and as efficient as possible. Structural analysis is what lets them find that perfect balance right in the middle.
When you boil it all down, this science gives us 3 huge benefits. Number 1, and this is the most important one, safety. It lets us be absolutely certain that our buildings, bridges, and vehicles are structurally sound. 2, efficiency. By optimizing designs, we save materials, we reduce weight, we save money, and we make everything from cars to airplanes perform better. And finally, 3, innovation. It gives engineers the freedom to test wild, new designs and futuristic materials in a virtual world totally risk-free, which just pushes technology forward so much faster.
So you see, structural analysis isn't some boring, abstract idea. It's the hidden hero working behind the scenes. It's what makes our entire modern world safer, our machines lighter and more efficient, and our technology more powerful than it's ever been.
And that kind of leaves us with one last really exciting question to think about. Now that we've gotten so incredibly good at predicting and preventing failure before it happens, what's the next unbreakable thing that this science is going to let us build?